After YouTube and everything? Oh yeah, got it. Good. So who's going first, Dave? You or me? YouTube and everything? Oh yeah, got it. So who's going first, Dave? You or me?
I'll go first. Can you hear me?
Do you hear me? I hear you, Dave. Do you hear me?
Yes, I hear you. Yeah. I'll go first.
Can you shut off the delayed video? You hear me? I hear you, Dave. Do you hear me? So I guess as you're preparing your screen, it seems like today's lecture is going to be a tag team with Dave going first and me going second, perhaps. And if I had to sort of describe today's lecture, I guess it is, for those who've never seen partial differential equations, that we need to understand a little bit about partial differential equations to fully understand climate models. And I guess Dave and I believe that partial differential equations come much later in most students' curriculum than need be. And it seems like there's no reason that they can't be introduced quite early in the curriculum. And so I guess in some sense, today's lecture is about PDEs ultimately so we could apply it towards climate science. Would that be a fair characterization of today's lecture, Dave? Yeah,
that sounds good.
Alrighty.
Okay. Hey, everybody. So as Alan said, we're going to look at an introduction to partial differential equations, of course, from the point of view of computational thinking. So how can we compute the solution to a partial differential equation? Actually, what does a partial differential equation even mean, and why should we care about them? And
I would say that computing really helps you understand what it even is.
Oh yeah.
So all those decades of Blackboard explanations of PDEs, just to me, is not as good as one little bit of computation.
Yeah, exactly. So what we're going to look at in particular are two types of processes, physical processes that are relevant to climate models, which are called advection and diffusion. And we'll just, today, I'll start at least looking only in one dimension. So, of course, we're going to go through what advection and diffusion are. So what is the idea? So let's think about the Earth. So far, we've been modeling the temperature of the Earth as just a single number that changes in time, a scalar that changes in time, capital T, the temperature, function of little t, which is time. And so we've written down these differential equations that describe how that temperature changes in time due to different physical effects, which are being heated by the sun and then reflecting some of that energy back, and then that leads to this, dynamics, which converges to an equilibrium temperature. And then we added carbon dioxide greenhouse heating, which is also a function of time. But but as we saw in the previous lecture, then that leads to, in the snowball Earth model, it leads to two possible equilibrium states. One where the whole Earth is at a temperature of 14 degrees Celsius, which is above freezing, so there's no ice anywhere. And another one which is sort of minus 50 Celsius, which leads to ice covering the whole Earth, because we only are talking about the average global temperature. But that's of course far, that's too much of a simplification, because we know that actually we should have ice at the poles and not at the equator. And so how can we model that? We are going to need to realize that the temperature of the Earth, well, it actually depends where on Earth you are. You're going to receive a different amount of sunlight depending where on Earth you live. And so, the equator receives more sunlight than the poles. It's being heated more, and so the temperature we expect to be higher. And if there's ice, then the albedo, the reflectivity there is going to be be higher than at the equator. And so everything suddenly becomes not only a function of time, but also of space, of position. And so the simplest possible way we could do that is to have the temperature T now depending on two variables, which we're going to call two independent variables, which are going to be time T and now space, which we'll call X. And so in this lecture, you can just think of X as being the latitude on the Earth, and everything is going to depend on how high up or down, how north or south you are on the Earth. And of course, so we're going to restrict to just one dimension, and we're just going to think that everybody in the band at the same latitude on Earth is at the same temperature. That's a first approximation. And later we can relax.
We had one exception for Boston, which is always colder than the rest of the latitude.
Right, exactly. So, that's a simplification again. So actually what we want to do is say, oh, well, actually the temperature depends on the latitude and longitude, and different latitudes and longitudes have different temperatures. And so we can generalize to that case once we understand the basics. We'll do that maybe next time. So yeah, so we want to calculate this temperature. We can call that a temperature field. A field just means that it depends, like a vector field, it has a value for, it's a function of different positions and times. And we want to calculate this temperature as a function of space and time, and it's going to vary in space and vary in time. And so what we're going to end up doing is, writing down a model that tells us, well, how does the temperature change? It changes because heat flows in some way, and heat flows from neighboring positions in space, right? If you think about the poles being cold and the equator being hot, we know that heat flows from hot to cold to try and equilibrate the sort of temperature distribution. And so we want to model that. And so we're going to have different temperatures, and we need to describe, well, we need to know how does heat actually move from one latitude to the next. So that's, and then we're going, so we're going to end up with, by writing down this partial differential equation that tells us the rate of change of the temperature and how that depends on neighboring positions in space and how it changes in time. And that's why and so we're going to end up with an equation that involves, changes in rates of change in time, so partial derivatives with respect to time of this temperature variable, and partial derivatives changes in space. Okay. So let's look at the kind of thing that we're aiming at. So this is a visualization of sort of the end product of this notebook. So here is a temperature profile, right? So this is a function of space. So let me add that label into this picture. So on the x-axis, we have space, which I'm calling x. And on the y-axis, we have the temperature T as a function of position. In other words, as a function of latitude. Oh dear. I have to put it on the correct plot. Okay, so space goes along here. In other words, here's the equator and here's the pole, say. And what we're drawing is the temperature, as we vary, the temperature is varying as we go from the equator to the pole. So this is not a very accurate representation of how the temperature would actually vary in that case. And also we're actually using a function which is periodic. So this value on the left at 0 is the same as this value on the right at 1. In most of this notebook will be using this sort of periodic rather as being, if we're just fixing attention to, say, one latitude, you can, oh, my internet connection is unstable. That's not good.
Yeah, I experienced a frozen Dave Sanders for about 15 seconds.
So, oh dear, I hope that's not going to be a problem. So yeah, you can think of just going around the Earth. So now think of X as actually going at one fixed latitude, going round. Then you have to join up to the same value. It's like an angle theta going round from 0 to 2 pi. We could think of it like that. Anyway, so this is a profile, which means a function of space, which describes the temperature in different places. And what we're now going to do is see how that changes in time. And so it's going to change in time due to these two effects: advection, which means that the temperature is going to be carried along by a fluid. So we're thinking of, if we think in the context of climate, we have two different sort of fluids around. We have the ocean, water, and we have the atmosphere, which is air, approximately. And so if we have this temperature, suppose this temperature is now the temperature at different heights in the ocean. If you think of, if the ocean now is moving along at some speed, or if this is a river and then you have a temperature across the river, if the river is moving along at some speed, well, this profile of temperatures will just move along with it. So let's look at that. So so U here, capital U here is a velocity of movement of this river. And as I move along, you see that this temperature profile just sort of shifts along with the movement of the river. The river is going to the right, and the temperature profile is also moving to the right. So of course, you could do this by just redrawing the temperature profile, at different positions. But if you notice, these grid, we're doing this on grid points. So one of the ways of solving equations like this is to discretize. We always have to discretize space in some way. We have to make it discrete. And one of the ways of doing that is to do these sort of grid points equally spaced along the spatial direction. And you can see if you look at one particular grid point like this one here, as I move time, the height of that grid point is just moving up and down. I should have actually put a dashed line on one of these things, and then you can see them actually moving up and down. And so this profile is moving across by, how is it doing that? By changing the values at each grid point. So what we need to do is work out how the value at each grid point changes in time, and that will change in time because heat is flowing along from its neighbors. And so that's,
I feel like I should be imagining people doing the wave at a sports event where people get up and down, but the wave
right
around the stadium.
So-called Mexican wave, yeah. Okay, yeah, exactly. That's a good analogy.
I thought it was the Boston wave.
Okay, I don't know. Okay, so that's one of these physical processes. So basically, if you now think about an actual ocean, you'll have ocean currents, which are basically kind of fixed. They're changing slowly in time, but they're sort of kind of fixed. And so if you think about some small little grain of sand or something, it'll just be carried along by this ocean current and will follow the sort of streamline along. And that's exactly what we're seeing here. So if I have a temperature profile, so different temperatures at different depths in the ocean, say, and the ocean, if the ocean were sort of moving along, all in the same direction, the whole sort of vertical ocean moving along, it will just follow this sort of velocity vector field, basically similar to the way it did in ODEs.
Dave, would it be easy for you to
carry it along?
Would it be easy, and if it's not easy, don't bother, but as you evolve time, could you keep the t equals 0 curve also on their
that's a good idea.
Maybe in some sort of backgroundy color like pink or something?
Yeah, so that's the initial curve. And as I move along, you see that this curve is sort of being shifted along.
Yeah, it's easier to see the shift now, especially if you only move a little bit. Before it would
that's
move a little, or else it'll go back to the end. But yeah, just move a little bit and let us look at it. Like, just go t equals a little bit more.
Here's a tiny bit. Yeah, so it's just sort of moved along a bit. How much? Well, it depends on the velocity, right? So it'll, in a time delta t, it'll move a distance u times delta t. The whole curve will shift along, and the way it shifts along, as I said, is by changing the height of these at each grid point.
Go to like 400 or 500 maybe time step, just as a. So
time steps here is just, this is just the number of the time step, and then up here I'm supposed to be plotting the actual value of time, and then for some reason it's not working. Oh, it's that in the wrong. Yeah. Okay. Anyway, whatever. So there's some.
Now it's easy to see that the orangey curve has, in some approximately discrete sense, is simply translated to the right.
Yeah.
It was kind of hard to see it before.
Right. No, I agree. Yeah. Thanks. That was a good idea. Okay. So now instead, let's see the other process, physical process, which is diffusion. That is how heat will spread out, even if the fluid is not moving. If there's some hot sort of spot in the fluid, it'll gradually spread out due to molecular motion, random walking. And so let's look at that. So here's a sort of hotspot. There's more heat in this region than there is in the neighboring regions. And so as I move time on, that heat should, I'm not doing anything because so I need to put some, this D changes the rate at which the heat spreads out. So now it's going to spread out, and you see that the hotspot is sort of shedding heat into the neighboring cold regions, and so the neighboring cold regions get hotter. And so the effect is to sort of smooth out this profile over time. And eventually you'll just end up with, you know, here we have a sort of slightly hot spot, here a slightly cold spot, and that will gradually sort of equilibrate, equalize, and we'll just end up with a sort of average temperature over the whole region that we started with.
Yeah, to me, it looks like you have like a heater around 0.5 and like an air conditioner around 0.3 or something, and a colder air conditioner around 0.7. And
well, not really. No, so I'm just starting with a hot piece and a cold piece.
All right, you don't want it to be a source.
I'm not heating or cooling after that.
Fair enough. Okay, so you that's the original temperature and it equilibrates.
Right. I had a heater and an air conditioner on, and then I turned them off at time 0.
And you let the room.
And I let the room.
That's a better way to say it. Yep.
Exactly. Yeah. So during the day I have my air conditioner on, and the window, you know, near the window is very cold. And then if I have a heater on the other side of the room, then I'll have this sort of situation where, I have a hot part and a cold part, and then if I turn everything off at night, then that'll sort of gradually the whole room will converge to the same temperature distribution, uniform. Great. So that's what we want to study. So how can we actually, you know, so hopefully it's clear what the physical sort of ideas are. How can we actually write down, you know, a model that describes how this happens and then solve it? Okay, so the first thing we have to do is just think about this initial temperature profile. So here's, you know, a curve, continuous curve in blue. And what we're doing is saying, oh, well, on the computer to represent this curve, I have to discretize it in some way. I have to represent it with only a finite number of data points. And one way to do that, as I said, is to just divide into equally spaced parts. And so what we're going to do is divide this interval 0 to 1 into equally spaced regions. I forget the number that I've chosen here. It's 20. So and each of these green dots is the center of one of those regions. And then at that position, we evaluate the function. We sample the function. And so we're left with these dots that we were just seeing at these positions. At each, so basically one value at each grid point, right? So we call these green dots nodes or grid points, or a mesh, and we're evaluating the function sort of at one point in each of those cells, basically. And so how can we think about this? One useful way to think about it is actually like this. We can think of that value that we're taking as being some kind of average over the whole cell. So here you can see the actual cells in these dashed lines. And here is the grid point in the center of a cell. And then the value that we're taking is the value of the function sort of evaluated at that grid point. And that's somehow representing some kind of average value over that grid cell. So, you know, you could say, well, that's not quite right because this is actually the largest value in the cell. So this is not really the average value. Okay, so there are various different ways you could go about doing this. Let's just take it as this piecewise constant function over the grid cell. So we have little volumes, right? If you're thinking about this as a fluid, we have these sort of fictitious volumes, and we want to know how does this value, this average value of the temperature change over time. So we're going to fix these grid cells and just look at one grid cell whose value is going up and down because it's receiving heat from one side and giving heat to the other side, or in the case of diffusion, it's giving, you know, each of them is sort of taking heat from its neighbors and giving heat to its neighbors.
And I'm going to echo what Dave said earlier in the lecture, which maybe I hope is obvious to everybody, that as one moves into sort of the more realistic climate models, the exchange of heat is instrumental to understanding, you know, what's happening on our Earth.
Right. Yeah. Okay. And in other physical systems, it wouldn't be heat necessarily. You would have other quantities that were changing. For example, this same ideas can model the concentration of some chemical, some pollutant that you have that's being produced in a factory or something. And then that pollutant will also be carried by the air and will also diffuse out in the same way. So the same mathematics, as often, the same mathematical equations model many different physical systems.
I hear perfume also, or any odor. In fact,
What did you say?
Perfume or anything you can smell.
Right. But also, the equations modeling how stock prices change are also very related to these equations. Okay, so let's look at advection, this being carried along by the fluid. So let's visualize what's going on. First of all, that will help to see what's going on. So here we have our fluid in a small, let's just think of a fluid moving in a channel. So there's these walls at height 1 and height 0 are a channel, the walls of a channel. And this blue box is one of these volumes that we were just drawing. And we want to know how much comes in and how much goes out. And here I've drawn little dots to represent the sort of amount of stuff. So you can think of the amount of molecules of a pollutant, or you can think of sort of the amount of heat. So these dots somehow represent the amount of heat in some not very precise way. And so as time goes on, what happens is that all of these dots, they live inside this fluid. The fluid is moving to the right. And so all of the things that are carried with the fluid, which we call tracer particles, they all move to the right as well. And so what we want to know is, in a given time step of length delta t, how many particles cross into this cell that we're interested in, and how many leave? And of course, some, as you can see, just stay inside the cell, right? So if I start inside the cell near the boundary for a little time, I'll of course just stay inside the cell. So what I'm really interested in is how many cross from one side of the cell to the other. So let's color those in a different color, and we'll see that for some particular time step, delta t, and depending on the velocity, this proportion of particles, exactly those particles which are closest to the boundary, they're the ones that will cross over in that particular amount of time. And these red ones over here are the ones that will leave the cell in that amount of time. And so that's just a little visualization to motivate writing down some equations that say the same thing. So what we want to do is some kind of time stepping idea, just like we've done before for ordinary differential equations. And basically, what we're going to do is sort of write down an ordinary differential equation for the amount of stuff, the amount of heat, or which is, so I'm not being very careful with heat, the amount of heat inside the cell versus the temperature of the cell. They're related by some constant that we won't even write down, the heat capacity. And anyway, so or you can think of concentration as well. How much stuff comes in, how much stuff goes out. So this is what you might call a finite volume method. I have a volume and I'm looking at fluxes or flows across the boundaries of this cell. And so we're going to use this notation. We now have two variables, so we need two labels for these cells. So we're going to call T sub I superscript n. That will be the temperature in cell number I at time n, or time step n. In other words, at time t sub n, and at position x sub I. Right? So I is just an integer that labels the cells. N is an integer that labels the times. And so you can think of a two-dimensional grid of positions labeled by I and times labeled by n. And so position I corresponds to, sorry? Cell number I corresponds to a position x sub I, and that determined by the width of the cells, and cell at time step number n corresponds to a time t sub n, which is n multiplied by the length of the time step, delta t. And so, for example, t sub I super n plus 1, that means at the next time step, so it's a time t sub n plus delta t. In other words, at the time t sub n plus 1. But if there's an I downstairs, then it's at the same position xi. So this represents the temperature at the same position at the next time step. whereas T super n I plus 1 represents the temperature at the same time, but the next cell over, right? So that's why we need to think of this two-dimensional grid with sort of positions on the x-axis and time on the y-axis. And the question is, how can we relate? What we want to do is say, oh, if I know all of the temperatures at the current time, then what will the temperatures at the next time step be? This is time stepping just like we did in the Euler method for ordinary differential equations. Okay, so how can we write down the equations that tell us how this temperature in a given cell changes over time? Well, it just changes, as we just said, because heat enters and heat leaves. And we need to just calculate how much heat enters and how much heat leaves. And so, as we were saying, the heat that enters is the sort of amount of heat that is living currently, that is currently at within a distance u, the velocity of the fluid, times delta t, the time step, from the boundary of one cell. And so everything in the next door cell that's within that distance will cross over. And so a fraction, a proportion, u delta t, and right. So that within that distance from the boundary, and then the whole cell has a width delta x. So we have a proportion u delta t over delta x of the amount in one cell that's going to move into the next cell. And similarly, the same proportion of stuff from the current cell will move into the following cell. And so once we write all that down, we get the following. How much heat will there be in my cell at time n plus 1? There'll be however much there was at the previous step, plus the amount that entered minus the amount that left. So the amount that entered comes from cell I minus 1, and the amount that leaves is going from the current cell into the next cell. And then this is this proportion that we just were talking about. So this is the equivalent of the Euler method in this situation. And you can see that the difference from what we did before is that now, of course, we have this dependence on the position as well, this I minus 1 and I. So the rate of change of the amount of stuff at my current cell depends on not only the value at my current cell, but also the value at the previous cell. And that's where we're going to get this spatial, we're mixing how we evolve in time with how we change in space. And that's what's going to give rise to this advection partial differential equation. Okay, but this is exactly what we're going to use actually to do the numerical simulation. Once we have all of the information about what are all of the temperatures at all the different cells at the current time step in this, in this two-dimensional matrix on one row of the matrix, we can then find all of the temperatures at the next row up using that information and this formula, this recurrence relation. Okay, and so how do we get out of that a partial differential equation? If we rearrange this equation, we can rewrite it like this. We've seen before that when we're doing these kind of continuous limits, we need to look at differences. And so here's the difference of the temperature at the next time step minus the current time step at one particular cell, divided by delta t, the length of the time step. And when we rearrange the previous equation, we see that on the right-hand side, we get this rate of change, or the amount of change, the difference in the x direction, in the space component. And so we're relating a change in time at the current site to the change, to how much the temperature changes between the neighboring site and the current site at the present time. And then when we take the limits as delta t and delta x go to 0 in the correct way, in a particular way, we get a derivative, right? This looks like a derivative in time, and this looks like a derivative in space. And so we're going to write those with this funny curly d symbol, which is a partial derivative. So the derivative only when you change time, and the derivative only when you change space of this function capital T that depends on these two variables. So this is the advection equation. It's a partial differential equation because it has partial derivatives with respect to more than one variable, independent variable. And we can write it without all this extra noise, just like this. So partial derivative of the temperature with respect to time, the rate of change, in other words, of the temperature at a particular location in time is equal to minus the velocity times the rate of change of that temperature with respect to space. And that is the advection equation, which is a partial differential equation. How are we actually going to solve that numerically? Well, we're actually going to forget about this or discretize this, these continuous derivatives again, and we'll get exactly back to this same discrete formulation that we came up with to start with. So, you know, it's more natural, in my opinion, in our opinion, it's much more natural to sort of formulate it in this discrete world. You can see exactly, oh yeah, there's some amount that was moving over to the next cell. You can really understand what's going on and then simulate it as we just did and as we're going to do. And then you can say, oh yes, well, if I take a limit in the right way, I get this partial differential equation. Of course,
still, it's a very good idea to kind of look at this a little bit and try to, you know, given that sort of Dave's just explained it, to kind of see it as, I mean, there are a couple of things to see. For example, I should probably, well, you can't see my mouse, but one thing is, if you're at a fixed time, if you're in a, you know, if time is actually frozen, then it's easy to see that, oh, well, you know, if I've got a profile, then I could take dt dx, and that's going to tell me how to drive forward into time now. Another thing to notice is that if my temperature changes quickly spatially, that is, if my nearby, if near to me the temperature is considerably colder or hotter, but anyway, a bigger change, then as I advance time, I'm going to get a bigger change at that original point. Right? And that's kind of what's being said by this differential equation, which, you know, almost looks scary, I think, sometimes to beginning students, but in the end, it's really only saying that my change in time is proportional to my change in space.
Yeah, and you can sort of think of it as, yeah, that's a good way of thinking about it. If you have a big change in space, a big gradient, a big, you know, sort of difference, then that causes a change in time that's bigger, in fact, because the heat is sort of trying to flow faster to fill in this sort of, you know, in using human kind of anthropogenic, what is it, anthropomorphic language. Anyway, yeah, great. So how can we actually solve this equation? Well, we just go back to this formulation in terms of the discrete quantities at each cell. And we have these explicit delta t and delta x, which are the time step and the spatial width of the cell. And then we literally write this in code in Julia. And so, but when we do that, we come into an immediate problem, which is that we have this ti minus 1. And so if you think about it, if we have a finite number of cells, and we're thinking about cell number 1, then cell number 1 is going to depend on the value in cell number 0. But cell number 0 does not exist because our arrays go from 1 to n. And so, although Ellen will talk about that a bit later. And so what do we need to do? We immediately see the need for boundary conditions. So we need somebody to tell me, well, what do you want to do at this boundary? If you think about a fluid, what you might want to do is say, oh, I'm only thinking about a pipe, and you know the pipe is finite, but I just have stuff coming in always from somewhere else. And so what you would have is some kind of flow in at that boundary, and you would take that into account. Or you might have a closed pipe, which had a sort of just a wall at the end. And so what you would say is, oh, well, the amount of flow across that pipe is actually, across that end is 0. And so you would take that into account. And what we're going to do to simplify things, as I said, is to say that our system is periodic. We have like a tube instead. And so the fluid is just moving round and round the tube in the same direction. And so we're going to sort of cut the tube at some point to say that, oh, this is the beginning of the tube and this is the end, but they are actually neighbors. So the beginning, so site 1 is, has as one neighbor on its left site 0, but site 0 is actually site number n on the other end. And so that will stick the two ends, join the two ends together and make something periodic. And so, So that's written, here's the Julia code for that. So we have what's called the bulk, which is away from the boundary, and then we have the boundary as a separate item. And so here I'm just literally doing a for loop over all of the cells in the bulk, and I'm just literally writing out that equation that we just had in terms of the cell number I, exactly just as the equation said. And then at the boundary, I do something special, which is that I treat the cell number I minus 1 as the cell number n on the other end, which just gives me my periodic boundary. So I'm making a function, advection, which takes in a vector t of the current temperatures, and we'll go through. And so this, similar, I think we've seen before, creates a new vector of the same length as t and the same type. And then I'm just going to fill in that new vector t prime, and I'm going to return it at the end. So it takes in one vector and it creates a new vector and returns that new vector. So that has some implications for you're allocating memory at each step. So there are ways that later on that we could actually avoid that allocation if we wanted to for efficiency. Okay, so what are we actually doing here? This is actually just like an Euler step in the Euler method for solving ODEs. This is literally an Euler step. We're just doing, function plus delta t times, value x of my variable plus delta t times f of x, the right-hand side, except that here f of x is now, x is now a vector of all these temperatures at different positions, and f of x is this formula that relates the different spatial components.
Let me point out that t prime here is not the derivative, but it's just the t as a time step.
Yeah, it's just the mathematical, t prime as in a new value of t.
Yeah,
I could have called this new t. Maybe I should just call this new t.
So that, yeah, see, I like that much better. Or next t or something like that.
Next t, yeah.
Yeah. Yeah, much better.
Okay, yeah, thanks. So, okay, so now what do we need to do? We need to just evolve this in time using an Euler-like method. And so right at the bottom of the notebook, there's just a function called evolve that just does that and stores the results somewhere and returns all the results. It's just like you've already written for the Euler method. Okay, so now we can just run it. So here, we're just calling this evolve function. We're passing in the advection function that does these steps. And we're saying which values of x to use, the nodes, the positions of the nodes in the x direction, what delta t to use, and what value of u to use. And then this is supposed to be the advection. And so we should see this profile just skidding along, just moving along at a constant speed. And what we actually see is that it sort of starts off apparently doing that. It seems to be moving along, but then as we go along, it actually turns out that it's also getting smaller in amplitude. In other words, it's also diffusing. And so it turns out that that is a problem and a sort of mistake, if you like, with this numerical method, with this numerical scheme that we invented, where we had this approximation of the partial derivative in space as this particular difference, ti minus 1. And so that actually leads to this combination of not only moving along, but also diffusing. And that's what's called numerical diffusion. We sort of introduced something we didn't want by using a numerical method that was sort of incorrectly designed.
So your equation was meant to only advect, and that's what the continuous problem would have done. But you notice that, wait, this thing that looks like diffusion is actually happening.
Right.
And that's
something I don't want right now.
Something you don't want. And
later on, I'll want to put diffusion in, but I want to control how I put diffusion in. And whereas this method is sort of spuriously producing diffusion when I don't want it.
So basically, I think what you're doing here is showing folks that, I mean, maybe the first computer science view of solving a differential equation is just do the average, the obvious finite differences. Like, oh wait, that is not going to be the desired result all the time after all.
Yeah.
But don't believe that's always that simple. There are fixes to it. I guess you're not going to tell us today the fixes, but this thing.
I'm going to tell you the fixes.
Oh, even better. But this thing is broken.
So one possible fix is to take a different approximation of the first derivative with respect to space. So here, instead of using ti and ti minus 1, we're using a so-called centered difference, where you take ti plus 1 minus ti minus 1, and you have to divide by 2 instead.
So you look to your left and to your right. It's not like, it's not just like you're looking to the left, which seems asymmetric anyway, right?
So it's a bit strange because we started off with this physical model where everything's moving to the right, but suddenly it turns out that to get a good numerical simulation of that, we actually have to do this sort of what's called upwind.
Well, I mean, if your what was it, u or something was negative, it would go to the left, right? I mean, it didn't really.
No, yeah, but I know, but I'm everything is moving to the right, so you would think that the value of the temperature at this position should only depend on the temperature of the.
My point, it's only going to the right if you think of the sign of your parameter as positive.
Yeah, but if the sign's positive, then it's always going to the right, and so I should only expect to have to look at the value on my left, but I actually have to look at the value on both sides of the temperature. Yeah, so that's kind of strange numerical effect. But once I do that, then I get advection to behave as I want it to behave, and it basically just does translate the whole profile along, and pretty much does what I wanted to do. So it turns out that advection in general is actually tricky to handle. It's an example of a hyperbolic partial differential equation, which basically is some kind of conservation law. I'm actually conserving the profile as I move along, and those are actually quite difficult to treat. Okay, should I talk about diffusion, or do you want to?
I think the second half of the lecture is not going to happen today. That's fine. Keep going.
Okay. So the other process that we were going to talk about was diffusion, and we've already actually sort of done this, which was in the random walks lecture. So it turns out that diffusion, this spreading out of heat or spreading out of concentration from high concentration to low concentration, is actually just a result of the random motion of particles. And so if you think about, if you have a lot of particles located in a particular place and not very many particles next door, these particles, the high concentration, they're all moving around at random. So some of them will randomly drift into the neighboring space. And so the concentration in the middle will go down and the concentration next door will go up. That's basically that effect. And so we actually did.
If cars on a highway do that also? Like if they're all bunched up, do they actually spread around? And
yeah, that's a good question. Yeah, there are plenty of models actually of traffic which use equations like this advection equation. It's a bit different because they can accelerate, right? They accelerate into space, so it's not really diffusion. Well, it's not random. The cars don't move randomly, so.
In Boston they do.
Okay, fair enough. And in Bangalore, they seem to as well. Okay. So we actually already started random walks in lecture 2.6, and we wrote down an equation that that's actually very similar to what we've just done. And in our current notation, it looks like this. The probability at site I at the next time step was half of the probability at the left hand plus the probability at the right hand. And that was because our particles were just jumping left or right. But if we also allow the particles to stay home, to stay where they are, then you get another term in here, which is the probability at the current site at the previous time step. And when you do all the details, you end up with something like this. So the temperature, so thinking of the temperature, the heat as being spread out by these particles, somehow the particles are moving around and they're somehow carrying heat with, in fact, heat is actually the sort of average speed of the particle. So anyway, the temperature at the current state at the next time is going to be actually given by this really nice formula, Ti minus 1 minus T2 times Ti plus 1.
So this is a different kind of equation now, right? You've made the model more complicated. You've done something here, right? Your T equation, your P equation are quite different.
Yeah, that's what I'm saying. They're not quite different. They're almost the same, except that I added a term here, which corresponds to the fact that I can stay in the same place. I don't have to jump left or right. I think it's basically just that. And so last semester, Grant Sanderson had a video that went into more detail to derive this equation, which is, again, very similar to what we've already done, but he has some nice animations that you can go and watch. And so when we now introduce again the fact that these cells are spaced a distance delta x apart, and we're taking time steps of length delta t, then we get something basically like this instead, right? So here we're basically taking delta t and delta x equal to 1. And now if we put delta t and delta x back, we get something more like this. And so that is, again, a recurrence relation that's telling us, well, how do we calculate the temperature at the next time step as a result of this spreading out of heat process, diffusion process. So then again, we can rearrange the equation by taking the right things. I think there's a factor of 2 missing. By taking the correct things to the, rearranging the equation, and then taking the continuous limit, just as we did before, and we arrive at this equation. This is called the heat equation or the diffusion equation, and it's now got a first partial derivative with respect to time, but a second partial derivative with respect to space. So it turns out
that was what I meant by that it seemed very like a different equation, by the way. Earlier I was saying.
Right.
Because before it was only first derivative.
Well, I think if you try and write this with derivatives, you end up with...
Oh, with a second derivative? Maybe you do. I see.
Yeah.
I see.
So this is actually a discretization of this. Let me find my annotation tool. It's remarkably difficult to actually annotate. So this combination is an approximation of the second derivative of capital T with respect to x, it turns out. And so when we take the limit in the correct way, we get exactly the second derivative. And so this is what's called a parabolic equation instead of a hyperbolic equation that we had before. And it models this spreading out effect that we've already seen. And so here it is again. Here we have our initial temperature profile. And as I change the time, the hot spots give up heat to their cold neighbors, and the cold neighbors absorb heat from their hot neighbors, and it's actually a very slow spreading out process. Again, because what's actually happening is there's a conservation law again. So this is what I mean by conservation law is just the total amount of heat is actually being conserved, is not changing in time, and so in order for this sort of slight hot spot to sort of fill in this slight cold spot, it actually takes a long time because the heat sort of has to move bit by bit, in space to sort of realize, in quotes, where the cold places are. And so it's actually a very slow spreading out process. But so if you have a very calm ocean and you have some pollutant being emitted somewhere from a I don't know, some pipe, the sewage pipe or something, if you have no movement of the water, it'll just sit there for a very long time and just gradually spread out. Whereas if you mix up the water by moving the water around, it will also be advected, and it will actually spread out and be diluted much faster. Okay, so so then we can just combine everything together. So the way we do that is by just calling advection and then calling diffusion, these two functions that we defined that implement exactly these time steps. We can just combine them into one advection diffusion equation, and then we get what we started with, which is both moving along and spreading out at the same time. And this is one of the main physical mechanisms in climate modeling. So that the temperature is being carried along by currents in the ocean, and there's this diffusion effect where it sort of gradually spreads out. And so we'll talk about that in a two-dimensional, more realistic setting. So if you think about, we'll talk about that maybe in a future lecture. Okay, I think that's the end. Any more comments on?
So I'll just say that I guess we'll do this on Monday. Monday, of course, is the last week of classes. But what I was going to do today, and I think it'll be kind of fun to do on Monday, is talk about a system where the discrete and the continuous both have physical meaning. And so I think that will help us, because I'm always very interested in connecting the discrete to the continuous. I think that's kind of a theme, one of the themes for this class. But we'll save that for next Monday, I guess. And then I guess on Wednesday, we'll do our last climate modeling that, for the semester for this course.
Hey, thanks everybody. Have a good weekend.